4 new examples to share tonight. So if you were at that previous presentation, the upfront material is going to be the same, but if you just hang with me to get through that upfront material, which sets the stage of what machine learning is, then I have 4 new examples to share with you. And so let me start with answering that question. What excites you? And oddly, I wrote down, I actually had 2, and I wrote them down before anyone started talking. And the first one was how it's going to impact transportation. I actually think cars and the way we get around today is horribly inefficient. There's just has to be a better way. And until we find that new way, we need to figure out a way to make the vehicles that we have smarter, more efficient, and maybe to the point where we don't even own cars anymore. We just summon the cars that we need. So I'm actually pretty excited about what we can do with artificial intelligence, machine learning in the transportation space to make that more efficient. And the other one that excites me is, I can't remember who said it now, I'm sorry I didn't write your name down, but it's the how we make that day-to-day home easier to live in. And it's something, maybe I shared this last time, but I have an aunt who has really severe rheumatoid arthritis. And so it's hard for her to get around. It's hard for her to open things. Light switches are hard sometimes. A number of years back, we got her an Alexa. And she doesn't like those things, not even a little bit. She's not tech savvy, doesn't understand, and was a little afraid of them. But we hooked them up to her lights. And we taught her how to get things like some of the news topics and weather from it. But most importantly, it turns out, were the lights. Because as she gets up in the middle of the night, lights won't be on. And so now she doesn't have to fumble for switches anymore. She can actually just ask Alexa to start turning on lights for her. It makes her living space much more livable. So how can we apply machine learning to keep people in their home where they're comfortable as long as possible? This is what kind of excites me about what we might be able to do with this technology. So that's how I would answer the question. All right, so let me start with the presentation. Again, I'm going to start with some introductory material, and then I'm going to dive into some examples. And this presentation, if you've seen it before, I really want this to be more hands-on, more showing you what it can do than just, talk about it. But we're going to have to talk a little bit to set the stage. All right, let's go into an introduction. A very brief history of AI. I mentioned this book before, but The Big Nine, I think, is a fantastic book if you want to understand the state of artificial intelligence today and who really owns it, who's driving most of the innovation, and the good and the bad that results from that. It's a non-technical book. So if you just want a good read on the state of artificial intelligence, great book, highly recommend it. And now we're talking about machine learning and artificial intelligence because it's the new shiny thing. It's the new kid on the block. But actually, the concepts for machine learning started decades ago. We just didn't have the compute resources necessary to make those academic studies and algorithms a realization, something that we could actually do something with. And we also didn't have the kind of data that we do today. As you all know, we are collecting data at a massive rate. And so the combination of having the algorithms and the mathematical background that we got in the 1950s and 60s, 70s, applying that mathematical rigor to our compute and data of today, it's that combination that's giving us the machine learning capabilities that we have. But a lot of the groundwork started decades ago. And it also I actually start to think, well, if the foundation of the new thing we're using today started decades ago, what are we doing today that decades from now they're going to look back on and go, this is where it started? I don't know what that is just yet, but I think like if that started decades ago, what are we doing today? That's going to be the next generation's decades ago technology that we're starting with today. So just some brief terminology. AI seems to, the term AI seems to have taken on a life of its own. It gets used a lot, and sometimes I don't think it gets used all that correctly. So AI stands for artificial intelligence. I like to think of the A, however, as augmented. So when I like to talk about artificial intelligence, I like to think of it as augmented intelligence, because right now it is really augmenting the human, in the middle, if you will. It's helping us make better decisions. Of course, there are times when the artificial intelligence is making all the decisions on their own. But right now, I like to think of that A as augmenting our human intelligence. But the artificial intelligence umbrella includes machine learning and then deep learning. Machine learning is really what we're going to be talking a lot about today, but I'm actually going to show you some deep learning examples as well. And this is where we will take some what we call traditional algorithms that require a certain set of data engineering to be applied to it. And then we apply these machine learning algorithms to it. The deep learning is a subset of machine learning and takes a slightly different approach, where the deep learning algorithms themselves figures out important aspects of data, where the machine learning actually still requires a lot on humans. And I'll talk about that in a second. But the big thing for our industry today, the big change for all of us, is that today we take, I'm working with clients today, this very day, where they've given me a set of my data set of inputs, and they told me what the output needs to look like, and I'm writing very purpose-built code to make that happen. That's what we usually do today. In the future, we're going to be told, here's the inputs that you're given, and here's the outputs that came with that. Now, instead of writing a purpose-built piece of software, we're going to train a machine learning algorithm to recognize those patterns in the data, so that when I see new input, I can map that to an output. So instead of writing code, we're going to be working on cleaning data, training machine learning models, making sure that the parameterization totally optimizes the algorithm. That's where the work is going to be. It's going to be less and less on actually writing code itself. And I'm going to show you how I can take that even one step further by looking at one of my examples later on. And so I like to ask, we get this asked of us all the time. People come to us and say, I have this problem, and I hear machine learning can solve everything, so I'd like to apply machine learning to it. However, so the question becomes, what problems can be solved with machine learning? And I tell them, any problem that absolutely, positively can be wrong sometimes. And this does surprise some of our clients, even to this day. Machine learning is built on probabilities. So at some point, it gets it wrong. And so the pushback that we get is, well, if it's wrong sometimes, I need my program to work all the time. Well, sometimes you do. If you are writing a financial application, and I'm going to move money from account A to account B, getting it right 99% of the time, they are right. That is not good enough. That's not good enough. You can't use machine learning in that example. But maybe that isn't your problem. Maybe what you're trying to do is just to get a sense for, work with a client on helping them understand which of their customers are likely to churn or go away in this coming year. What are those attributes of their behavior that they can recognize ahead of time to keep them from churning? So if they don't do anything, those people are probably going to leave our clients. But maybe we can at least identify some of them and maybe get ahead of that game. So in that case, the business problem says, yeah, it's okay to get that wrong sometimes. Money, you got to get right all the time. But figuring out who might leave your company or what customers might be leaving, that if you can just get 60% of them correct, that's a win. So it depends on your business around if it can be wrong or if it can't be wrong. And if it can, what is your tolerance for how wrong it could be? So let's talk about being wrong. Here's an example, and this is an example of the number of people that are going to be diagnosed with breast cancer. So there are roughly 270,000 new cases in women, roughly 2,700 new cases in men. So let's say that you have a machine learning algorithm that is 97% accurate in determining whether or not somebody has cancer or they don't have cancer. Does that sound good or bad? Well, until you know more information, I don't think you can't really say just yet, because what is it about those 3% that you got wrong? It comes down to, well, how did you get those 3% wrong? So you have to start thinking now about, well, I have the true positives, I mean, I actually truly diagnosed you with cancer correctly. And then the true negatives, that is, I absolutely positively got it right that you don't have cancer. But there's other two quadrants for false positives and false negatives. That's where I falsely said you did have cancer, but you really did not. And the other quadrant is I falsely said you did not have cancer, but you did. So of the 3% you got wrong, we need to know how are the false positives and false negatives distributed, because it's a whole lot better to be told that you falsely have it, but you actually don't. I know that's scary, but at the end, it's better that you don't, because the worst scenario is to be told you don't, but you actually do. So we need in that medical case, we need to make sure we minimize false negatives. And if we have to adjust our model with our parameters so that we skew it to give us more false positives and false negatives, that's what we would do. And that's part of the job of tuning that algorithm. So when I said we're not going to write code anymore, we're not. But we're going to look at the results of our models, and based on our business problem, the problem we're trying to solve, how do I tune it so when I am wrong, I'm wrong in the best possible way? So machine learning comes down to the art, and it totally is still art here, is the art and science of giving computers the ability to learn to make decisions from data without being explicitly programmed. And that's what it all kind of comes down to. It's going to look at the data to find patterns in data that it can apply to new data that it hasn't seen. Sometimes when people ask me, like, how would you describe machine learning? I think of it as a really good probabilistic pattern matcher. It can see pattern in data that you and we will never see the difference between row 1 and row 2 ever. And yet the machine learning algorithm figures out the subtle nuances, the differences in each of those rows. So we could actually say row 1 belongs to class A and row 2 belongs to class B. It is super great at finding patterns. So let's talk about roughly the two types. Oh, and by the way, since Pat, I'm looking at my screen here. If a question comes in, you think I need to answer right away, feel free to jump in. All right, so we're going to look at two types of machine learning. There's machine learning and deep learning. We'll talk a little bit about the differences between the two. So let's say we're trying to, we have a classification problem. And let's say the input is going to be a picture that has a car in it. It has a car, a bus, and a motorcycle, or one of those three. And we want to know when we send that picture of car, bus, motorcycle, which one is it? I want to know if it's the car, the bus, or the motorcycle. So we in both examples of machine learning and deep learning, I start out with the exact same inputs. In machine learning, I go to the next step of what we call feature extraction or feature engineering. And this is typically where the data science person, the data engineer, is going to get involved. It's going to look at the data that it has available to it, to the problem, and start to clean it. So we make sure we have all the data and it makes sense. It's all within the right ranges. We're not missing any data. But I also might engineer some new features, depending on exactly what those features are. Or we might look at the data.
Pat, pardon me. Salim, or pardon me, Kareem has asked if you would be willing to maximize your screen. I think it's challenging to view the information you're showing.
I don't know if it's going to help a lot. I think that's almost as best that without losing, it's probably the best I could do. And actually, that would be better for me. Is that okay? Is that better?
Why don't you use the Windows Zoom? Oh wait, is this a Mac?
It is. Did you?
I don't know how they do that.
You
Well,
just set that up.
Kareem
Didn't you?
Kareem is saying that's better.
Okay.
Thanks.
Boy, that does my whole thing. All right. Thank you, Pat. Okay, so there's two types of machine learning and deep learning. Going back to the machine learning, the top path here, the difference here is that we're going to have a step of feature extraction, feature engineering. That's where the human, the data scientist, stops, takes a look at the data, and potentially creates new data that feed into a machine learning model. And in this case, I'm showing something like scikit-learn. That we will then train models based on all that data to tell me if the output was one of my car, motorcycle, and I've forgotten what I was looking for, the other one. Bus. The difference, however, with deep learning is that it's a completely different way to look at this particular problem. In deep learning, we literally have layers of nodes where each node is taking in all these lines are inputs into a node that go through a mathematical process, and every node feeds every other node downstream. And this process just repeats itself through the entire network. Everything between the inputs and the outputs, those are called hidden nodes or hidden layers. Because the inputs we can see, because I actually have to physically create them, and the outputs I can see because that's what I've asked it to predict. But the number of actual layers in between the input and the output can be any number. And within a layer, you can have any number of nodes. This is where that whole training of a model and figuring out the exact model architecture, it's a bit of science, a bit of art. But the key difference here between machine learning and deep learning that I want you to take away is the amount of feature engineering or feature extraction typically is a lot less than with machine learning, because the deep learning process figures out what features are important and which features are not. It can figure out based on how it's got to maximize the accuracy, or in some cases a loss. We'll talk about that one later too. That'd be minimizing a loss if I wasn't clear. Maximizing things like accuracy, minimizing things like loss. It will figure out exactly what weights to give to each one of these lines coming into a node. And it does this by going forward. It starts at the inputs. It runs through all these nodes, and then it measures how bad it was. How wrong did it get the answer? And based on that error, it does something called backpropagation, and it updates all the weights. And it's not random, it's all mathematical, but it updates all the weights on all those lines. And then it's going to do it again. It's going to run all that data through, and it's going to say, well, how well did I do this time? And then it's going to go all the way back, and it's going to keep doing that until it gets down to an accuracy that you can live with your business problem. But I didn't have to do a whole lot of feature engineering. But what I did need is a lot more data and potentially a lot more time for it to figure out at the exact weights to use for the data that I have. Now, if my input data changes, you have to go ahead and retrain that entire thing again. If there's another term called narrow AI, if you've ever heard that one. And the other thing that think about and take away here too is machine learning, it's really good at a problem. We train a model to solve a thing, like figuring out if there's a car in a picture. But once I have the model trained for that, I can't use that to then figure out what customer is going to churn. So it's not general artificial intelligence. It's very narrow for one problem. Pat, I see your hand is up.
Yes, Kareem asked, pardon me, in the chat, is deep learning only constraint to neural network as shown as an example?
Boy, I guess I'm going to say no. This is a typical way to do it. This is a type of deep learning network, but there are other networks that we could use. Things like, particularly for images, something called, it's a big word I know, but it's convolutional neural networks. And that is yet a slightly different architecture. But at the end of almost every convolutional neural network is at least a small deep network like you see here. So this usually plays a part in a lot of deep learning. It may not be the entire particular approach that's taken. So I would say, is it constrained by neural networks? I mean, yeah, I guess so, but not only this architecture. There are other architectures that we could use. So good question. All right, let me continue on here. Let's just talk about machine learning for a second. 3 different major types of machine learning. Supervised machine learning. That means I've got my data, and every row of data has what we call a label to it. So if I'm trying to figure out if a picture has that car, the bus, or the motorcycle, every picture has a label that says that's the car, or this is the motorcycle. I know the answer to it. It's almost like you're getting the test, and on some of them you get the answers, and on some of them you don't get the answers. Those are what you're going to be training and testing on. Unsupervised learning I'm given a bunch of data, but I don't know what label to associate that with. So why would I use that? Well, that's pretty handy when you want to do things like figuring out how is this data clustered together. I got a bunch of data on customers, and I don't know what label or how to bring customers together, but I asked the machine learning model to look at the data and let it decide which other customers are most like which other customers. And the machine learning model, again, figures out the patterns and figures out which one of those are close together and which are far away. Reinforcement learning is yet completely different. This is where I'm going to start with basically, it's used in games, and I don't necessarily have model or data. I have a system for this machine learning model called reinforcement learning to figure out the best thing to do in that system. For example, if I'm driving a car, then you can train it that every time I do something good while I'm driving the car, like I'm turning and I don't actually go off the road, you give it a reward. You say that was really good. If you go off the road, you give it a negative reward. And eventually, after enough cycles through that training loop, it figures out that, hey, when the picture of the road looks like X, I know the right thing to do because I keep getting positive rewards for that. So reinforcement learning works off a reward system that says these are good behaviors that you've learned and these are bad behaviors. Don't learn those bad behaviors. All right, so I'm going to switch over to some examples now. We have until 7, right? So we have about 45 minutes, so that's probably good. But I can take a quick break here if there are questions.
I always wonder in reinforcement learning, like how you actually code what gets rewarded and what doesn't get rewarded. It's kind of obvious in scenarios like autonomous vehicles. If you don't hit something or kill someone, that's +1. I never really understand how they do that in kind of Skinner-esque. I don't understand how they do that in actually in other environment. It looks like you had an example there.
I did. So I ran through this one. I'm pretty sure I ran through reinforcement learning last time. Well, I had this to the list at the end if I didn't. So here's a simple game where the green square has to, it's told nothing about the environment except that it can move one square in any direction. And the goal of walking around this environment is to find, I'm sorry, the blue one is the blue one is what's called the agent. This is the thing, this is the thing playing the game. This is going to move around. It needs to find either the green square or the red square. And in every time through this game, the red and the green move to different locations. The blue square is told only, here is the distance between the blue square and one of these, but it doesn't say which one it is, and the blue square and the other one. It's only told the distance between them. And after a while, it starts to realize that, hey, when I get really close to this one, good things happen. And I should try to get as close to it as I possibly can. But when I get really close to this one, the red one, bad rewards come my way. I don't want that one. And so it will actually learn to avoid it. You know, let's just run it because it is such
oh, there it is. So all you have to do is give it, you don't even have to give it what you use as the distance measure?
It's just a number to this particular algorithm. So every time you move, I actually take a negative reward. Let me just fire it up because I can talk while it's fired up. I think it'll still work. Here we go. All right, and I know it's not crisp lines anymore. So the blue one is just randomly walking around this game. Every time it moves one square, I give it like -1 negative reward, saying I want you to minimize the number of moves. If it ever finds that green one, it gets like 25 reward points. If by chance it finds the red one, it gets minus like 500. I really give it a bad negative reward. But right now, it literally is just randomly moving. Now, every time that blue dot is in a square, it knows at that moment in time, the calculated reward for making any move to the next square.
So
it's doing that.
Moving randomly, you don't have to tell it use a Euclidean distance or a Manhattan distance or anything. It just moves randomly and it knows I hit this one and I didn't get a reward, so I'll never hit that one again.
Exactly.
Okay.
So that doesn't. All I'm telling it is I am telling it a distance, but it doesn't know how it got it. It just gets a number. So now it's going through these games really fast, so it's learning super fast. So every 10,000, it'll stop and do one more game. So look at this. After 40,000 iterations of the game, it's starting to learn how to find the green one really well. And now we're going to think, now we're at almost 50,000 moves, and it almost never gets it wrong. Now, it may not be the most efficient path, and it might get stuck, but it'll get itself unstuck eventually. So it's learned that, yes, see how it went around the red one? Because it said, man, when I got really close to that one, I got too much negative reward. Don't go there anymore. So it's learning from the environment.
Pat,
the good
Kareem
things
has a
and the bad things.
question.
Yes.
Reinforcement learning sounds like unsupervised learning. Is the difference based on how we train it?
Oh, wow. That is such a great question. So it is unsupervised because I don't actually have labels or I don't have the answers to it. But the algorithmic approach is very different. So it is, I guess you're right. It is unsupervised because I'm not going in with any of the answers. But it's learning as it's going. It's learning from the environment that it's operating in. So it actually doesn't start with any data either. It starts with nothing. It doesn't know anything about the squares or what distance is good or what distance is bad. It's all based on what they call a reward function. So every time you make a move, you get a reward.
There is no concept of supervised or unsupervised in reinforcement learning. It's, in fact, if you want to think about it, the real taxonomy is there's supervised learning, there's unsupervised learning, and then there's reinforcement learning.
Right, and that's what this was really trying to show.
Oh, yeah.
Really three distinct types of machine learning. But if you wanted to break it up, there definitely is not supervised for sure. But yeah, you're absolutely right, Adam. Thank you.
There's another one called semi-supervised and self-supervised.
Yes.
Sometimes it gets really nuanced and you can drive yourself crazy.
Yes, totally agree with you. Yes, that's why let's just stick to 3. So that basically that's reinforcement learning. I'm reinforcing behaviors that I wanted it to do in the future. So good question. All right, let's talk a little bit about, I'm gonna swap that one out now. Now I know I talked about facial recognition. I'm gonna do the best I can here, but I actually am gonna need my entire screen. I'm bringing up other windows at the same time. So I'll do the best I can. So I'm going to talk about facial recognition. I'm going to show you some examples of actually performing some facial recognition. And there's a lot of different ways to do this. This is just a way to perform facial recognition. It just happens to be, it's not the most sophisticated, it's not the most accurate, but it's something I can do on my laptop in the matter of a minute. I get enough data from a single picture to do some facial recognition. And I wanted to show you how easy it is and the basic concepts that go into it. And this came from another presentation that I give. So you'll see I have the overview. I still really love that book. Here's the controversy though, is who owns your face? I don't think that question's legally been answered yet. Because when you go to a baseball game, the back of your ticket says if you came in and you used this ticket, you give baseball the right to show your face. My mom says she does. That's awesome. Great. Love it. You give them the right to show you in the stands. So if you're just walking down the street, do you own your face? If someone's got a camera, can they use that to figure out who you are? I don't think that the legal system has caught up to that one completely just yet. And if you don't know this one, if you've heard about the social credit scoring in China, they are doing something like this right now where they actually are watching you. They know who you are. They know if you're the one honking your horn or if you're not doing something socially acceptable. And much like the reinforcement learning, they're going to take points away from you. And your ability to move throughout the country is going to be impacted by this. And a lot of this has to do with facial recognition, knowing who you are. All right, so a little bit of background. This, as far as I could tell, where we really started to see a lot of algorithms able to do the facial recognition came in around 2001. So it's not that old, if you ask me. And where it really became possible for us to do it on our computers or even like little mini Raspberry Pis is using an algorithm called the histogram of oriented gradients, or they call it HOG for short. And basically what that does is we are going to find the differences in brightness of a face and use those differences to figure out things like where are your eyes and where's your nose and your chin. And I'm going to show you what that looks like in just a second. So for facial recognition, we're going to break it down into the following. We're going to first, you find all the faces in the picture. This particular algorithm finds 68 what they call facial landmark features. There are other algorithms that do a lot more. Some will do X, Y coordinates along with Z, so they can figure out like how big your nose is, how far back your eyes go. This one just does X, Y coordinates, so it's not as sophisticated. But what we do is we encode those 68 points of your face. We run through a deep learning model, and that creates a 128 valued vector or array of data that represents your face. Now, what do those 128 values mean? I have no idea. I don't think anyone has any idea. You ran it through a machine learning model, you put 68 in, you got 128 out. So then we can compare. Once I have this array of numbers, I can then use that to do basically a high school distance calculation. On a new face, like if I show my face, it can do a distance calculation to see which of those vectors, which of those arrays I'm most like. So here we go. First step is find all the faces. And again, we're going to look for, so the picture's broken down first into a black and white picture. And then for every pixel, we want to find where the gradient, meaning from the lightest part of the picture to the darkest part. And we're going to take 16 by 16 pixel squares. And in that 16 by 16, where is the darkest and where is the lightest part of that picture? And it ultimately looks a little something like this picture shows us here. So there I am on the left. And when I run it through the histogram, it then creates this black and white of nothing but those vectors that we just talked about. Let me see if I can get this to actually work. Oh, I got to come off of this one. There we go. Hopefully you still see my screen. There I am. Hello. So that is the histogram of oriented gradients, or the HOG, for the video feeding my camera right now. And we as people, we can look at that and see where the face is at. The key is going to get a computer algorithm to figure out where the face is at. And I just want to show you, like, so that must have been really hard to do, right? Well, the libraries and the frameworks are so good these days that really all I did is I asked skimage, which is scikit-learn from the first part of the presentation. It has something called a hog routine, and I just passed it the image that I got from the video feed, and it told me, it figured out the histogram of oriented gradients for me. These frameworks are super powerful. So it's just, I think it's Sir Isaac Newton that said, you know, if I should see further, it's because I stand on the shoulders of giants. We are standing on the shoulders of giants when we use these frameworks. So now let's take a look. It will use the histogram and then try to locate faces inside of it. And this one is fairly simple. Well, there's my face, but where's my other one? Oh, there it is. There I am. There I am. So you see the original video feed and then the histogram feed, and it's drawing the box around what it saw as my face. So it found that face, and everything else around the room, it said there were no other faces except for this one. And this is how you do that. Again, very little code. Now let's take a look at those facial landmarks that we were talking about. I think I did show these last time, but what it's going to try to do is find these 68 points around your face and draw them on your face. And it's these 68 points that go in, that go into the machine learning algorithm to give you that 128 vector out. And everyone's going to be slightly different. Everyone's landmarks, they're going to be close, but they're not going to be the same. Oh, come on. There we go. So there are my landmarks. So it's using that histogram of oriented gradients to figure out the exact box for my face. Then within that box for my face, it goes through and figures out, like, where are the eyebrows? Where's the nose? How's the chin shaped here? And it's going to take these 68 points and generate the 128 value. And you probably thought that was really hard to, but it really isn't. These libraries that we use make it so easy these days, which is like wonderful and scary all at the same time. So here's what it does: is it takes the face in with the 68 points. It runs through a bunch of convolutional layers. It's basically a convolutional neural network. And here's that fully connected layer at the end of that convolutional layer. That this is the fully connected network that we saw earlier. That's what I was saying. Even if you have a slightly different architecture, like a convolutional neural network, you usually end up with a fully connected network at some point. And the output, you know, in the example I showed, it had the 3 bubbles for the output. In this case, it has 128 bubbles. And we're going to use all of those values. Those values are going to be just probability numbers. And that's sort of what, I just took some of the numbers out of this. There's 128 values. But if you were to just print what those values look like, this is what they look like. 0.09, minus 0.09, minus 0.14, plus 0.14. There's no way, again, this goes back to the great pattern matcher. There's no way we as humans could look at 128 these numbers and go, oh, well, that's clearly Pat. There's no way we could do it. And this is how hard that was to get the numbers. I use a package called face recognition, pass in the image, I get my bunch of boxes, and then I tell it to just get the face encoding in each one of the boxes. And in this case, there was only me, so there was only one box. All right, so now let's put it to the test. Now we're going to say, I took a data set of people that I got from my very favorite website on computer vision called PyImageSearch. So he already had a set of some of the Jurassic Park characters. So I'm going to use that data set. I then added my own, pictures of me in different times and different places, with glasses, without glasses. And these are all the people that I have. Everybody from the Jurassic Park and then me.
Pat?
Yes.
May I ask you, I should have done this earlier. Dan Tavaldi has vision loss, so if you'd be willing to explain visually as you walk through, which
Oh, yes.
you generally do anyway, Pat, but my apologies.
Yeah, no, thanks for the reminder. Thank you.
That's on me.
Yes, no problem. And thanks for the reminder. Okay, so what we're going to do now is I'm going to take a single picture of me that, let me see, this might be my LinkedIn profile. I can't remember what's out there anymore. So I took those pictures that you saw earlier. I'm just going to scroll back a little bit. So I have these 6 pictures of me from whenever I did this, years ago. But they were not the LinkedIn profile picture. So then I'm going to take the LinkedIn profile picture. I'm going to run it through that same algorithm to figure out the 128 values that represent my face. And then I'm going to ask the algorithm to figure out, well, all the faces that you've already stored numbers for, who do I look most like? And I hope it's going to say me. And so here's what it comes back with. And the big long number is basically the distance. So of all the pictures that are in there for me, it says that, yes, in fact, I am closest. This picture of me from LinkedIn is closest to other saved pictures that were labeled as Pat Ryan. But who do you think? So it's actually going through and looking at all the pictures. So who do you think I look most like if I scroll back to the Jurassic Park characters? Do you think I look most like Alan Grant, Claire Dearing, Ellie Sattler, Owen Grady, John Hammond, or Ian Malcolm? It'll tell you who you look most like. Even if you think you look like Ian Malcolm, of course I think you look like Ian. It's, the hair. So who do you think I look most like? Well, the algorithm will tell you that I look most like John Hammond. I didn't see that, but based on the numbers, based on the way the 68 points define your face, it says I look most like John Hammond. Now let's try. Let's try another one. I'm going to go back up real quick. Sorry about that. I should have had this all in place. Here he is. There it is. Sorry about that. All right, so then based on all of that, it comes through and it says, yes, indeed, you are Pat Ryan. But the other thing I wanted to point out is, let's say I had a picture here. It's also, let me see if I can get my face in there too. So from the video feed, it says I'm Pat Ryan. From the picture, it says I'm Pat Ryan, but it also says this other guy is unknown. It's the distance of that person's face, which by the way is Keith Emerson from Emerson, Lake and Palmer back in the 70s. We don't know who this person is. Let's fix that.
Love it, Pat.
So I grabbed a picture of Keith Emerson, roughly the same age. I mean, he has pictures back from the 70s, but it's not the same picture, but roughly the same era. So I didn't want to be too far off. I'm going to use this one picture and I'm going to train. First of all, I'm going to generate additional test images from this one image. And we can see we now have Keith Emerson in our data set. And that's what the pictures look like. All I did is took the one picture and just changed it a little bit. And I'm going to feed that into the algorithms. So now I'm going to create what they call facial encodings for all of these new pictures of Keith Emerson. And I'm running this in real time. I'm not pre-baking any of this. So there it did. It ran all, I did 10 facial encodings for it. So now we're going to run this one more time. It's going to load in the new facial encodings. Oh, come on. There we go. So it still recognizes me. Yay. But now if I hold up the picture, oh, no way. There it is. Keith Emerson. And the guy in the back, it's figuring out there's a face there, and it says, I don't know who that one is now. But it figures out that, let's kind of come back a little bit to get better picture. It figures out now that Keith Emerson is standing next to me.
Bravo.
I think that's kind of cool, and like so little lines of code and so fast we can do facial recognition. It's not perfect. You saw it go back and forth between unknown and Keith, but wow, that was super simple to do. All right. Okay, I've got another one that I want to get. Oh, this is going to be good. Okay, I'm going to go back over to my machine learning. And for this one, I'm going to talk about, oh, there it is. I'm going to talk about pose detection. And so pose detection is a little bit like facial recognition in that with facial recognitions, we were trying to find 68 points on your face so we can determine what your face looks like. For pose detection, oh, wrong one. Oh, it's not blowing up any bigger than that. Maybe I could do that for now though. For pose detection, I'm showing a picture of a woman, and what's been superimposed are all what we call the body landmarks, not just facial landmarks, but body landmarks. So it figures out, for example, where your wrist is at or where your elbow is at, roughly where your shoulder blades are, or your waist is located. And so it can then start to create this frame of a person, and everyone's frame is going to be slightly different. And so I'm not going to use this to identify necessarily a person, but I'm going to use it to identify the pose that that person is taking. And now once we know the pose, well, we could do really, I think we can do super cool things with it. Like, for example, what if you're doing physical therapy? My shoulder was frozen. It happens from time to time, and you could barely lift your shoulder up. Well, you could, if you had something like this that would help understand, well, when is Pat's shoulder above horizontal? The pose detection can do this. It's almost like having your own physical therapist without having the physical therapist there. So we're going to use another library. Again, we're standing on the shoulders of some of these giants that have created these algorithms. So we're going to use a media pipe pose detection. That's the library we're using so that I could get the raw points of where my shoulders are at, where my arms are at. But then we're going to do something with it. So how does it work? Well, this is what the points, the body landmarks look like from the media pose library. So it's going to tell me where all those points are located. And what I want to do, I want to create something called the YMCA dance detector. Now, if you remember, I guess I'm doing a whole 70s thing, Emerson, Lake and Palmer. Now I'm doing the Village People in the YMCA. If you remember the YMCA, that was where you raised your arms up in the air with a Y and an M and a C and an A. We used to do all kinds of crazy things with it. I wanted to use this library so it could tell me, well, when am I actually doing those poses? And let it tell me. So I thought, let me create a machine learning model that takes those points and identifies what does a Y look like? What does an M look like? And then I can run that through a real-time video. So for example, when I trained it so that when I held my arms up in the air in the shape of the Y, it told me all those red dots on the right. So there's a picture of me on the left with my arms over my head. And on the right, there's that same picture, but I plotted in red dots all the XY coordinates that the media pose library told me my arms were. And I did move around a little bit. So I went back a little bit and I turned, because you want to generalize. You don't want it to learn exactly it has to be in this position, but it's roughly that position. And that's why it looks like a cloud. But it's using those points to say, if your arms ever look like that, that must be a Y. And if you ever look like like this. So I have another two pictures. On the left is a picture of me with my fingers on my shoulders. And on the right, all the XY coordinates that the media pose library said were related to this particular pose. And you can see this one is super noisy. Again, I was moving back and forth, and I was shifting a little bit, but that's what an M looks like. And believe it or not, I had to go train more M's because it was so noisy. It didn't do a good job of M's initially. So if I look for a C, again, I'm showing two pictures. One on the left is me doing a C, which is, gosh, how do I describe it? One over my head and one coming up like I got this jaw. So making the letter C. And again, on the right are all the XY coordinates that represent my pose for the letter C. And we're going to do the same thing for an A. So this picture on the left shows me with my hands over my head and my fingertips touching. And on the right, the same picture with all the XY coordinates. So I'm just taking all those XY coordinates. Oh, I forgot one more. And there's dance, of course, because you're not always doing a YMCA. So I just took a video of a lot of frames of me dancing. And this is what that looks like. So you can see where it picked up the shoulders and the arms and the wrists are all down by my midsection. All right, so then I took all that data and I collected it into a table, and you can see this very first one, all these numbers represent the M, right? That the M is where my fingertips were on my shoulders. But is there any way that you or I could figure that out just by looking at the numbers? No way, couldn't do it. But I trained a machine learning algorithm to do that. So now I'm doing all this live coding. It worked an hour ago. You never know. It has to be able to be wrong sometimes. All right, so now I'm capturing the video feed, live video feed of me in my office, and I'm superimposing the media library points, the body landmarks on it. And you can see it's got my shoulders, it's got my arms in it. As you see, as I raise it, it's going to a Y, and if I bring them down, it's going to dance. All right, so here's what we're going to do. We are going to see, and I'm glad this is recorded, we are going to see as I do the dance, the YMCA dance, if it can detect, look up in this upper left-hand corner where right now it says dance. As I'm going through the YMCA dance, you should see this change as I'm doing the Y and the M and the C and the A.
Adam, please play your Village People recording.
I got it. Here we go. This is all done in real time. It's taking these points as I'm dancing at this very second. And it's running it through the machine learning algorithm and telling you, oh, it's taking all those new points that it's never seen before, and it's saying, these new points for Pat dancing today, is this most like the Y or the M or the C or the A? It says, for 99% probability, that's a Y. So I think this media pose is super cool. Because now we can do so many things with it. I know I just did it for this goofy dance, and it was fun to do. But there's some serious applications for this. And the one that really does come to mind are things like physical therapy. If I need to know how I'm doing in getting a shoulder healed up, or maybe knees or hips, you can use these pose libraries to give you a sense and to give you that feedback. And yeah, things are going well, keep going. Or maybe it's going to say, hey, it's been 2 weeks and you haven't gotten to the 70 degree angle or whatever angle you need to get to. Let's schedule a doctor's appointment. Something's not going right. So there are very serious applications of this type of technology. All right, I'm gonna, so it's 6:42. I'd like to try to get at least one more example in here. And this is inspired by our very own Pat Maher. He posted out to our company Teams channel, just said, "Hey, did anybody see that 60 Minutes on deep fakes?" And it wasn't that like kind of scary and cool all at the same time. So I thought, oh, deep fakes, that might be kind of fun to talk about here. So I'm going to spend a little bit of time talking about deep fakes. Now, most of this I had to pre-do because the computing power that you need, it's at least for the very simple, it's tens of minutes. For the very complex, it's hours. But let's just talk about deep fakes. Like, what is a deep fake? So a deep fake is where you could take basically the face from somebody and you superimpose it onto another video or image such that it's indistinguishable, that it's not the source face. So you can basically make people do things and say things that they never said or did. It's kind of cool. It's really scary. And when I dug into this, I was a little surprised at how easy. I know there's apps out there that does this, but I wanted to use some open source machine learning models and build upon them and see what I could do. It turned out to be a lot easier to do than I thought, which is a little bit scary. So there's a couple different categories of deep. There's actually a number of them, but we're going to talk about two. One is just the face swap, and that's literally where I'm going to take my face and then superimpose that onto somebody else's face in a way that you can't tell. It's going to be seamless. It's going to be a brand new person. And the other one is what they call puppet master or face reenactment. That's where you're going to allow things like the lips to move, the eyes to blink, eyes to move, a head to move back and forth. So that takes it to the next level yet again. And so how does this work? Let me see if I can do this. I'm going to zoom in a little bit. So I have a picture that shows a little bit how the face swap works. Okay, so they have these things called encoders and decoders. Think of these as an encoder as a compression tool, like zip compression, and the decoder as your decompression. So what we're going to do is we're going to take these faces. This time it's Hillary and Angelina Jolie, and we're going to train our compression algorithm to compress those images down to what they call it the latent representation of face A. Basically, think of it as the minimum amount of information I need to represent face A, or face B in this case. And then I write a decoder that'll decode that minimum information to reconstruct the original image. And this is where machine learning comes in. Now it says, well, how bad? Remember I talked about that? Like, how bad did you get that reconstruction process? And depending on how bad it is, it'll then go retrain the internals of that model, and it'll do it again so that when I reconstruct it, it's almost perfect. Now I'm going to do that. I'm going to train the compression side of it, the encoder on face A, and the decoder for face A. I'm going to train the encoder for face B, the compression algorithm, if you will. And I'm also going to train the decoder or the decompression algorithm for face B. And then I'm going to swap them. I'm going to use the encoder for face A because that knows how to make face A's really small. But I'm going to use the decoder for face B. So it still uses that small data representation of a face, but it deconstructs it or reconstructs it in this case, decompresses, reconstructs, so that it takes it knows how to basically map the face A to what face B would look like on that other person. And now I have this completely new person. It's kind of crazy. It gets even crazier. Let me see. Yep, good. So I'm going to show you an example of a professional one. So on the left is the original Forrest Gump. On the right, it's where they've superimposed or created a deep fake with Keanu Reeves' face in this particular image. And I took each of those scenes and I just stitched them together and tried to line them up as best I could so you could see the difference side by side. And this is a professional quality. And take a look. You wouldn't know the difference if all you saw was Keanu Reeves on the right. You would think that was Keanu Reeves in the film. It's almost indistinguishable, which is the scariest part of this whole thing. so they got all the facial expressions that somehow melded on frame by frame by frame, the way the eyes open and close, all done frame by frame. It just mapped it perfectly. So that's what a professional one looks like. I'm going to show you what I did in like 10 minutes of compute power. All right, I'm gonna take this picture of Sheriff Andy Taylor. If you remember Mayberry, I guess am I going back to the 70s again? Is that 70s? It's got to be 80s, 70s. So there's a picture of Andy Taylor, who's the sheriff of Mayberry, and I'm going to take that's a static image. That's just one image. It doesn't move. I'm going to take this video.
By the way, Pat, you're going back to the 60s now.
Oh, thanks, Pat.
Pat, I can't hear your videos. I don't know if anybody else can.
Oh, no, you're kidding. Ah, thank you. No, it's really important to hear it. Can you hear me?
Yeah, I can hear you.
Okay. Okay. We should have, darn, I should have tested this. This is Safari. So what if, how about now?
No.
Yeah, it's interesting. Steve's saying he is hearing.
No. Maybe it's just.
But I'm not, Brian.
Oh, but not in the notebook. Steve said he can't hear what's going on in the notebook.
Oh, I see. Okay. Well, all right. We're just gonna have to continue on with the time we have left. All I said was, I'm not Sheriff Andy, but I am. But this is what I want you to see. All right, so now what I've done is I have another video here where I've taken the rendered video. It took about, like I said, 10, 15 minutes to render this video. I took the static image of Andy, and I took the video that you just saw, but apparently didn't hear, and I created a deep fake. Now watch, compare and contrast. Remember that the picture of Andy was static. And here's what that turned out to be. I know you're not gonna be able to hear it, but so here's, I don't know if you, I know there's a lot to see there, but did you see the way, I mean, the head didn't move, it was a picture, but yet the head's moving with my head. The lips moving with my lips. And if you saw it, if you look carefully enough, the eyes were moving.
Yes.
And this is just literally, this is the first, what they call it, first order model for deep fakes. 10 minutes of compute, a video I created and a static image, and that's what it generated. So to me, it's really scary. You could do so much with not a whole lot. But yet it's still incredibly cool what you can do. I remember watching Harry Potter when they had the newspapers and the people moving. I thought that's kind of cool. It's real.
Oh,
it can do it.
Yeah.
So it's actually something that we could do today. All right, I'm going to do, okay, one more. I'm going to talk a little bit about style transfer. So this is I think this is another really cool one. Very similar to deep fakes, how we're taking content from one source and content from another source and bringing them together. In this case, it's a little less scary and definitely looks super cool. So for style transfer, here's the idea. I want to look at one of the images and I want to pull out all the style information, but I don't want any of its content. But I want to know, like, what are the blues and how is the image created? And then I want to take a content image. So I have another image here of the Chicago skyline. The first one was a picture of Starry Night by Van Gogh. And then I have a picture of the Chicago skyline. And what I want to do is take all of the style information from Starry Night and apply it to the content of the Chicago skyline and bring those together. So how does it do that? Well, essentially, all machine learning algorithms, they either want to maximize an accuracy or they want to minimize a loss. And so for style transfer, essentially what we're trying to do is create a single loss function that will look to minimize the style information in the resulting image. It'll also look to minimize the loss, the content loss in the resulting image. And then it'll try to minimize something called total variation, but just think of that as noise. It's going to try to minimize the noise. So remember, this is a balance, right? So it's going to try to strike that balance of minimum style loss, so I get as much of the style as I can, but minimum content loss, so I can still recognize Chicago without having a lot of noise in the picture. So now I'm going to create, I am going to use these different pictures and apply them to my video camera. And I probably have to take my video off for that. I'm still here though, don't go away. All right, so now it's taking this picture at the bottom, which I think is called Candy, the real-time video feed, and going through the style transfer algorithm. So on the right, there is the resulting image where it tries to pull as much of the style from the pictures as it possibly can, while keeping as much of the content as it possibly can, to result in basically a live video feed as though it were painted like those pictures.
So cool.
And depending on the algorithms you use, I'm using ones that have been trained in a way that I can do it in real time. The really super good ones, you have to do it in a batch mode. But even for real time, I mean, this is amazing. My whole room now is Starry Night.
That is amazing.
Oh, and I got the scream ready. My version of Scream. But it's just super cool, the things that you can do with these machine learning algorithms. And I know we got 5 minutes left. I'm just gonna let it ride. So so that's, anyways, I wanted to present you guys with some new and slightly different examples than what I did before. I hope this was interesting. I hope you found it exciting. I think this field is amazing. I love it. Mind blown. That's kind of cool. Any questions or?
Someone's typing, Pat.
Okay.
As always, Pat, your knowledge, passion, and presentation style is non pareil.
Thank you, Pat. And these are all libraries. They all run on my machine. Well, I should get back. The deepfake one, had to use some compute hardware and a GPU, and it's a little more involved. But most of these things, they just run on your laptop. If you just need small data, small example sets. So my point being is it's super accessible for all of us to get into and just play around with.
Well, Pat, yes, Kareem, I believe Brian creates the link to the recording, and we will get that to you. And Pat, you can read. Terrence Baker is asking.
So my favorite place for something like this, where it's machine learning, deep learning, and computer vision, is piimagesearch.com. Let me just go right there. Open up a new tab. Piimagesearch. Oh no. Imagesearch.com. I think this person's He has blog content that is free. If you wanted to get, he also has a lot of stuff behind a paywall. And I think I have almost all of his books. They're a little pricey, but oh my word, are they good. And the code examples are great. But the blogs themselves, he gives you all the code. The blogs are free. You want to just learn about OpenCV contours. He goes over what it looks like. And then later on down here, you'll see code examples of how to actually do it. So PyImageSearch.com is just wonderful for computer vision stuff. I pull a lot of my presentation stuff from him, or a lot of things. He inspires me to create some of these examples. So PyImageSearch.com.
Pat,
Great question.
Kareem had asked earlier or early on whether this was a weekly meeting, or he seemed to be interested in a successive scale of learning. And I noted we could possibly set a Teams discussion group, or something along those lines if there was enough interest. So I don't know, Brian or Pat or Adam, what you guys may think.
And so were you thinking something along the lines of like maybe taking one of the examples and just doing a little deeper dive on it? Because that's possible.
I'll let Kareem ask that, but I think he was speaking more broadly.
Okay.
And
yeah, but
Terrence is saying he's interested as well.
I'm sorry, was that Kareem? Are you jumping in?
Yeah, sorry. Yeah, so either or would be nice, really. I think deep dive into one of the examples would be pretty cool as well. So whichever one is easiest, really.
Okay, sure. I mean, I think it'd be super fun to see if we can't get one of the examples like working on your machines. And then you can take it from there and just play around with it and change it and explore. That's how you learn.
Yeah, so group, maybe Brian and I and Pat will discuss offline briefly and figure out a logical approach to reach out and have Pat, as his time allows. Obviously, Pat's billing clients, of course, for many hours, but again, I understand, Kareem, and Terrence, your interests. So I know Pat's flattered, and he's a professor at heart. So we'll figure out a way to reach out and make that happen.
That sounds great. Would love it.
Great. Well, we're a couple of minutes after the hour. Brian, I'll let you take us home, as you do so well.
All right, yeah, thanks everybody, and thanks Pat. And I will, as soon as we're done here, I will process the recording and I'll put it up. It might not be till tomorrow that I have it out in a link, and I will send it out to everybody. All right, thanks again.
Thank you, everybody. I really enjoyed doing this. Thank you for having me. I love doing it. Hope to see you all again.
Wonderful, Pat. As always, thanks. Thanks, everyone. Have a great evening and weekend.
Good night, everyone.
Good night.